Hi everyone, my name is Jingjing and this is Zichun. Today we are going to present a paper and the paper's name is Search What You Want, Barrier Penalty NAS for Mixed Precision Quantization. So before we start to talk about some key ideas in this paper, we start from something we are familiar with, CNN. Deep convolutional neural networks has earned remarkable performance in computer vision tasks like image classification, object detection, and etc. We know if we want to utilize CNN models into devices with less memory and computational resources, one way is to quantize floating point weights and activations with fewer bits. However, it often causes accuracy to drop when all CNN layers share the same quantization bit width. So currently, more and more platforms like FPGA have supported mixed precision computations, which assign different quantization bit widths to different layers. And this helps accomplish a higher accuracy with fewer bit operations. Furthermore, many real applications set a hard constraint of complexity to their bit operations, but it is computationally expensive since we need to determine appropriate setting from all possible candidates. Therefore, to better elevate the problem just mentioned, one way is to use the weight sharing approach. This incorporates the BOP cost as additional loss term to search the mixed precision models. However, there's still some problems. Invalid search. Invalid search, meaning when the framework seeks a trade-off between accuracy and the bit operation constraint. The process has to repeat many times by trial and error for tuning the BOP's cost and loss weight. This process is time-consuming and often leads to suboptimal quantization. The second problem is that importance factors corresponding to different bit widths in each CNN layer often have similar values, which makes it hard to select the proper bit width for each layer. The third problem is the balance of high weight and low bit training strategy. High bit and low bit training strategy often cause unstable training. So to solve these three problems separately, this paper proposes three corresponding solutions. Soft barrier penalty is to help bounding the search in the valid domain. The prop 1 regularizer is to distinguish the importance factor. Distribution reshaping method is to train a model with uniformly distributed weights and no long tail activations. We will discuss them later in detail.
Before talking about the detailed techniques, I want to give a brief overview of the related work and background. In high bit quantization, explicit loss error aware quantization, or ELQ, uses incremental strategy to fix part of the weights and update the rest in training. Half-wave Gaussian quantization, or HWGQ, uses clipped ReLU to remove outliers. And parameterized clipping activation, or PACT, further proposes adaptively learning and determines the clipping threshold. For lower bit quantization training, the first one is in the slide focused on extremely low bit quantization. Bayesian-based methods is to optimize 1-bit CNNs, and the two-step method is also used to train the low bit quantization. As we just mentioned, mixed precision quantization can efficiently recover the performance at the same time consuming less bit operations. Mixed precision search is to search the mixed precision model with high accuracy by using less bit operations. There are several neural net architectures search or NAS methods. One is RL-based method, which is to collect the action reward into the loop and use this data to train and to search the model. Single pass uses evolutionary algorithms to achieve high precision and satisfy the constraints, but at a great cost. Either method has its own pros and cons. In this paper, the research is applying weight sharing NAS methods into mixed precision search. Compared to this to the DNAS, which is the first to introduce in this method, the new barrier penalty-based NAS, or BP NAS, has the following three features: barrier penalty strategy, probe 1 regularizer, and distribution reshaping strategy. Now let's talk about some details of mixed precision quantization search. Problem of mixed precision quantization search is to find a set of quantization parameters for different layers so as to keep the original model's accuracy as much as possible while fulfilling some complexity constraints. Conventionally, we denote a weight as W. For each W, we linearly quantize it into B bits. And alpha is a learnable parameter. For weight, clamp function is used to truncate the value into range minus alpha to alpha. For activation, the clamp function should truncate the value into range 0 to alpha. And the dot means doing the rounding operation. Cast the problem into an optimization problem. We have MP denotes to be a mixed precision configuration for network N. The loss function is to obtain the loss on the validation set. By this process, the updated MP is obtained. Besides, we usually have additional requirements about the complexity and memory consumption. We introduced a BOP formulation where FLOP is the number of floating point operation in layer L. For convenience, this paper actually refers to BOP to average bit operations as formulated on the right side. And this BOP needed to be bounded by an upper bound constraint Bmax. Why do we need NAS for mixed precision quantization? Due to the large cost of training a mixed precision model and a huge mixed precision configurations, to select one to satisfy all requirements is being practical. So weight sharing in NAS is applied. First, construct and train a supernet SN. As the figure shows, for example, between node V1 and V2, there are several candidate space operations. The output is calculated by assembling all the edges, and Pij is the importance factor and can be calculated. Second step, after the supernet has been trained, the mixed precision model can be sampled. Finally, retrain a sample model to gain a better performance. However, there exists a problem, a trade-off between complexity and accuracy with either large or small lambda. So in order to achieve a higher accuracy as well as efficiency, barrier penalty is added for the NAS method. It is used to bound the mixed precision search within a feasible solution space with a differentiable form. The key idea is to develop a regularizer to punish a training with extremely large loss. The right side of the equation is modified for differentiation purposes. It looks like setting a barrier at Bmax for the model. This is why it's called a barrier penalty regularizer. Other than that, the sampled model estimation is reasonable only when the importance factor Pij for each layer is highly selective. In other words, the importance factor should go to 1 and the others should be very small over to 0 in order to be distinguishable. To meet the goal, we introduce a probe 1 regularizer. As the formula shows, this function fx achieves the minimal value if and only if there exists a unique xj to which 1. Here we are not going to into the detailed proof in this short talk. After using a regularizer, the importance factor gradually becomes either 0 or 1. We'll see the results later. Let's summarize the BP-NAS algorithm here. There are 3 steps on this: training a supernet, sampling mixed precision form of the supernet, and retaining the mixed precision model. If anyone remembers, there's still one problem that hasn't been solved, which is the unstable training. So the paper uses distribution reshaping to alleviate this problem. For each weight W in the I layer weight, it uses a clipping method to reshape the weight to get uniform-like distribution. If you're interested in the robustness of quantization work with distribution reshaping, you can check more in the reference papers.
After talking about the methodology, let's look at the performance of the experiment on different data sets. The first one is implementing ResNet20 on the CFAR10 dataset. The BOP constraint is set to 3, 3.5, and 4 bits for 3 experiments. there are some settings for training the SuperNet. Randomly split of 60% samples to training data and others as validation set. With batch size of 512, use of SGD optimizer to train weight, use Atom optimizer to train architecture parameter theta. Retraining for 160 epochs and use cutout in the data augmentation. The results are shown in this table. For example, compared to the HAWQ, which achieved 92.22% accuracy with 64.49 times compression ratio, BP-NAS gains 92.3% accuracy with much higher compression ratio up to 81.53 times. We can tell overall, BP-NAS can reach the higher accuracy. At the same time, it can maintain higher compression ratio. An experiment with ResNet 50 on ImageNet dataset, with random sample 10 categories with 5,000 images as training set and 5,000 as validation set. Retraining for 150 epochs with batch size of 1,024. We can see that either having constraint of 3 bits or 4 bits, the BP-NAS has achieved the best accuracy of 75.71% and 76.67% separately, which earns the best accuracy when comparing under the same constraint. For experiment with ResNet 50 fast RCN on COCO detection dataset, with use of ImageNet to pre-train the backbone and fine-tune the RCN for 27 epochs, with batch size of 16 on 8 GPUs and use of SGD optimizer. The results here is baseline, is 0.3.3 MAP. It's much better. It's better than the FQN result. Since there is still a job to get a better result with the constraint equals to 4 bits, experiment further implement BP-NAS to search the mixed precision for fast RCN. It achieves 0.358 MAP with the compression ratio up to 64.76 times, which is better than the original one. In this slide, the ablation study is showing the significance of BP-NAS and the Prop1 regularizer. Result shows on the left side, with the barrier penalty, the model is effective in achieving higher accuracy while keeping less average bits. The graph on the right side is showing with the Prop1 regularizer, those similar importance factors are differentiated and the red curve tends to be 1 while others go to 0, which makes it easy to distinguish the factor.
To summarize this paper in general, 3 ideas are discussed. A novel barrier penalty neural architecture search is introduced for mixed precision quantization, which ensures all search models in the valid domain meets the requirements. To meet the requirements, Prop1 regularizer is proposed to differentiate importance factor in each layer. The distribution reshaping strategy will make the training much more robust and achieve better performance. Extensive experiments data also validates this research topic compared with the original NAS. This new BP-NAS can not only speed up the search process, but also reach higher accuracy. And thank you so much for listening.